Okay, ECE 205 students. This lecture is designed to make up for the lecture that you missed due to the unexpected absence of your instructor. So we'll go ahead and get started just to try to keep the video time to a minimum. So this lecture is all about reintroducing the ideas of span and linear combinations, linear independence, the stuff we need to define a basis. So we'll start by talking about this recap example. So here we want to show that given any vector y in Rn, this set L sub y, which is just a notation we're using to define the set of all of the scalar multiples of that given vector y, is also a subset of Rn. So in order to prove something like this, you have two options. One's not a very good option. You could just apply the definition of a vector space and show that Ly on its own is a vector space, and in particular, it's a vector space that lives inside of Rn, thereby it's a subspace of Rn. Now you should never do this. It's technically what you need to do by the definition, but we do have the awesome theorem that is the subspace test. So if I steal this from here, we'll just talk about how to do this in written form, and then I'll give you the nice, cute little written solution, which is the way that you should write your final answers. So here, we need to show that for any given y, and the fact that this says for any y means we need to start with an arbitrary y. So we start with let y as a vector just be an element of Rn. Okay, so we don't know what it is, that's all we know. And we also should formally define this, and so we can say and let Ly be the set of all the scalar multiples of y, for S is in R. Now, there's fundamentally 4, depending on how you want to think about it, properties we need to mention to use the subspace test. And if you don't mention any of these, then your work isn't complete and you will lose marks accordingly. So the first thing we need to do is argue that Ly is not empty. So we need to think about an element that's always going to be in here regardless of what y is. Well, we know there are real numbers, right? Therefore, just pick any real number, we know that scalar multiple of y will be in the set Ly. Now the classic number to pick is 0, because typically we show that Ly is non-empty by showing it has the 0 vector. So we can say, hey, look, 0 is a real number. So 0 times y, which we know the 0 in the underlying field times any vector always gives us the 0 vector, is going to be an element of Ly because it satisfies the definition, this term up here, of being in Ly. Yep, done, non-empty. The other thing we need to do, that's kind of a subset of this, is we also have to mention that Ly is a subset of Rn, right? Sometimes you have a vector space Ly that could legitimately be a vector space, but it's not actually a subset of Rn, therefore it fails to be a subspace. So we're just going to say, note that Ly is a subset of Rn. Now it might seem silly that we have to do this, but again, we have things like R1, perfectly valid vector space, but it's not a subset of R2, therefore it fails to be a subspace. Right? So because of things like this, we always have to check that, and you have to explicitly mention it. Now, the next two things we need to do are show the closure properties. Now, we have options here. In the theorem for the subspace test, we called these points 2 and 3. You can prove them separately, or you can prove them together. Here, I'm going to show them together, and in the notes, I show them separately, but you have your choice of which one you want to do there. Okay, so to do this, I have to start with two arbitrary vectors, x and y. I'm not going to call this y, I'm going to call this x and z. just because I'm using the symbol y already. Let these be elements of Ly, and let some arbitrary scalar. We don't use a in the question statement, so I'm going to say let a be in the real numbers. Our goal is now to consider x plus a z, and we want to show that this linear combination satisfies the requirement to be in the set Ly. Okay, so now we have to ask ourselves, what do we know about x, what do we know about y? Well, I know x is in the set Ly. Yeah, since x is in the set Ly, I'll do this as an aside. Since x is in here, we know there exists a scalar, I'll call it Sx, such that x is equal to Sx times the vector y. Yeah. And by the similar argument, since z is also in Ly, we know there's another scalar, Sz, such that z is equal to Sz times y. Now here you should also probably mention the data type, I should say, is an element of the real numbers. Formally that's required, but that's the idea. So we know these two facts here, and I'm going to use these facts on this line. I can replace x with Sxy. A stays as A. Z, I can replace that with Sz times Z. Okay. Now, since we're in the real numbers, and this is a very concrete vector space, we know what the vectors look like, we know how they work, we can just use general properties of things that are in Rn instead of appealing to the axioms. Now, in my work, for the version on the slide, I will appeal to the axioms because there's a more general version of this theorem that I'm kind of highlighting that the general version holds. But here, we can clearly say, well, this I can oops, sorry, I messed up here. Sorry about that. This z should be a y. Bad students not yelling at the screen telling me. Yeah. So here, since these are two vectors are y, I can factor out all the scalars, right? We have axioms that allow us to do this. And in particular, in the real Rn, we know that we can do this. So I can rewrite this like that. Now, what do we know about this constant? Well, we know the real numbers are closed under the operations of addition and multiplication. So we know this thing, don't know what the number is, but I know it's a real number. Yeah. Therefore, we can conclude that this vector x plus az satisfies the condition to be in Ly. Okay. Now we're not done, right? All of this work is sufficient to show that it's a subspace only if you've done the work prior to prove the subspace test. So we need to cite the subspace test as a theorem since we are using it in this argument. So we end with a by the subspace test. By subspace test. The result follows. So we can say Ly is a subspace of Rn. Yep. Okay. Normally I'd ask for questions, but video lecture. So here's the version in the slides. If you want, you can pause the video and read this here. This particular proof actually works if I replace Rn here with the arbitrary vector space V. Right? Here I'm only using over a field R. So here I'm only using properties that arbitrary vector spaces have. Right? So you can take your time, see that, examine that version of the proof, but in particular, since this one asked about Rn, this work is sufficient. Okay. Now we're going to well, in theory, this is review, so we're going to re-go through the definitions of span and linear combination. Now, these definitions are of fundamental importance for linear algebra because at a fundamental level, linear algebra is studying vector spaces, And spans and linear combinations are really how you get a lot of vector spaces. So, definition of span. A span is of a collection of vectors, S, so this finite sets, in some vector space, F, over a field, V over a field F, is simply the set defined by this. So what we do is we take all our vectors, v1, v2, all the way up to vn, we scale them by any scalar ever, and we then add them up together, and we take the collection of all the possible spans that come out of this. Okay, so that's the idea of span. It's just I'm taking a linear combination, adding up all the vectors together with some scalars, and taking the collection of all of the possible results. Now, for very important reasons, we're also going to add a very particular convention. We're going to define the span of the empty set to be the set containing the zero vector. Now, mathematically, you can kind of look at this and say, well, if the set's empty, right, if there are no vectors, there is no linear combination, so why would anything be in the span? And that's a valid question, right? But the reason why we choose this convention is to make a lot of the subsequent theorems significantly nicer. If we throw away this convention, then when we start talking about the dimension of a vector space, we're going to start running into a bunch of edge cases. In particular, this vector space that has just the identity element in it would have an undefined dimension if you wanted like the span of the empty set to be anything other than this. Right, so this is for convenience. Make sure you know it. But yeah, so it's mostly just so that we don't have to have a bunch of asterisks everywhere and start sounding like lawyers with all the extra clauses we have to make classic theorems become true. Okay, so we have some nomenclature regarding span. These are just ways that we're going to use words. Make sure you kind of memorize these and internalize them a bit, because we will freely use these various combinations of these nomenclatures throughout the rest of this course, essentially. So, the set span of S is said to be spanned by S. We can also say this by saying S is a spanning set for span S, or more simply, S spans S, and this thing up here, I already used the nomenclature, but it's called a linear combination. So a linear combination of a collection of vectors is simply a sum of this form. Okay, so next slide time. Let's look at some examples. Determine if this first vector is in the span of these next two vectors. Okay, so how do we go about tackling this kind of a problem? Well, what this problem is really asking us to do is to determine if there exist coefficients, say A and B, in the real numbers. Here it's going to be the real numbers because these are real vectors and that's a real vector. You could go over the complex numbers, but it just makes the problem more complex, pun intended, without actually increasing the scope, right? So we want to know, are there coefficients A and B such that this vector, 1, 2, 3, can be written as A, 1, 0, 1, plus B, 1, 1, 0. That's the goal. Yes, no. Yeah, answer the question that way. Now, generally, you could turn this into a matrix problem, right? So one option over here is I could rewrite this as 1, 0, 1, 1, 1, 0 times AB. And I could try to determine if this system has a solution. Kind of the classic way of doing this is to augment the matrix and then row reduce to see if you can get a solution that way. Now here for this particular problem, you don't have to do that. Now you can. I'm Xing it out. That's not to say it's wrong to do so, but it's slow to do so. And there's a better option. If I look here at the third component, this third component of the equation, if you will, this equation individually reads out 3 is equal to A times 1 plus B times 0. This just tells me A is 3. Now, if I use this fact, I can rewrite the problem. 1, 2, 3 is equal to... Now, if I multiply this by 3, I get 3, 0, 3 plus B, 1, 1, 0. Now, we know the last line will hold, so we just need to deal with these two components of the vector, if you will. Now, if I read off the second equation, that lets me solve immediately for B. Come on, click. My mouse. Sorry about that. So here, the second line tells me 2 is equal to B. Okay, so I know A is 3, I know B is 2, and if I look at the first equation, that then would read 1 is equal to 3 plus 2. And that's clearly not true. Not even for small values of 5 is that true. Therefore, we can conclude here that the answer is no. Since it just said determine, really, if you just say yes or no kind of thing, you're good. Since we don't have homework, if it's a quiz and you can see that pretty obviously, you can say no. It's good to give a counterexample though. So if it said determine with justification, you need your counterexample. But if it just says determine, technically, you can just say yes, no kind of thing. Okay, let's look at the other one. Determine if this is in the span of that. Okay. So here, really, the only difference between these two, let's make that there. So really, the only difference between these two is that the first question was involving normal vectors, and this is just involving a different type of vector. Yeah. So it's the same question, right? Do there exist coefficients A, B, C? In this case, since these are real vectors, since the coefficients are real, we're going to use real scalars. Determine if there are A, B, and C such that the first vector, my 2x squared minus x minus 3, is equal to linear combination of the next ones. B 1 minus x plus our C 1 minus 2x minus x squared. Okay. So here, you can actually multiply these out like normal polynomials and then put it in standard form. So if I look here, my x squared coefficient to this side comes from only this term, so I get cx squared. Hey, I already know c is 2. My x coefficient comes from, well, I have a minus b from this and a minus 2c from this component times x, plus I have a plus b plus c. Now, two polynomials are equal if and only if their coefficients are equal. So I can read this out as 2 has to be c, minus 1 has to be negative b minus 2c, and minus 3 has to be a plus b plus c. Now, this system is designed, well, I know it was designed this way, but this system is such that you can just use substitution, right? So the first equation tells me 2 is equal to c. The second equation, if I plug these together, says minus 1 is equal to negative b minus 4, or b is equal to, so I add the 4, so I get 3, and then I put a negative, so negative 3. And finally, I can back sub the values of a and b into the last equation, and I can rewrite that as minus 3 is equal to a plus b, b is negative 3, plus c, c is 2. So here, I can solve this for a. So 3, when I add this 3, I get a 0. When I subtract that, I get minus 2. So I have successfully solved the system, the 3 circled bits there. Therefore, the answer to this one is yes. It is in the span because I wrote it as a linear combination of the vectors that, yeah, I'm spanning. Okay, normally I'd ask for questions again, but you guys kind of can't ask questions currently. So let's go on to the next proof. So if S is a subset of vectors, or set of vectors, v1 through vn, is a subset of a bigger vector space V, then the span of S is a subspace of that vector space V. Now, this is actually a generalization of the problem we started the lecture with, right? Here, if I changed this to be an arbitrary vector space V, right, this is just dealing with the special case where I span, or dealing with the span of only a single vector Y, right? So that's actually why I used that example way back when. So for this one, we'll just talk about the proof and general strategy things. Basically, the only things you need to actually do here are apply to the 3 steps that are required for the subspace test. Okay. So first, we want to talk about non-empty. So, well, I don't really know anything about this vector space V. I don't know anything about these vectors v1 through vn. So I have to think what vector is always going to be in S if this, or in the span of S, if the span of S is a subspace of V. And the answer is always Mr. Zero Vector. So zero vector is going to be, or can be written as this linear combination. Just 0 times v1 is the zero vector, all the way to 0 times vn. That's the zero vector. If I add a finite number of zero vectors together, I get the zero vector. Formally, to prove this, induction's kind of the way to go, but this one's sufficiently obvious that this will work, that this would be sufficient for your work. So from here, I can conclude that it's non-empty. We also need to include that it's a subspace or subset, which I didn't do in this version of the proof. I will upload that and put it in the slides for completion. But the argument for why it's going to be a subset is that all of the elements of the span are written as linear combinations of v1 through vn. The vector space V is a vector space, so it's closed under linear combinations. That's what axioms C1 and C2 tell us. Therefore, the span of S will be a subset of V. I will add that explicitly in the notes when I upload things. Okay, so now what I want to do is argue the 2 closure properties. Now, I could do these together, but here I'm going to separate them just because there's a number of moving parts, and I think it might be useful for some students to see them separated. So if these vectors x and y are in the span of S, then we know, by definition, there exist coefficients, x1 through xn, y1 through yn, such that x and y are written as a linear combination of the vectors v1 through vn. So explicitly, that's what we know. Okay? Pause the video if you want to think about that a little bit, but that's what it means to be in the span of S. There are these coefficients where this is true. Now what I want to do is show that x and y, if I add them together, that results in something that can be written as a linear combination of v1 through vn. So I want to look at x plus y, add them together. Well, what do I know about x and y? I know they can be written just like I did up here. Right? So I copy paste those guys down. And now, through our vector space axioms, we know that the order of addition of vectors doesn't matter. So I can pull this vector all the way over next to the y, or the other x1, v1, do that for all the components. And I also know we have a distributive rule for scalar multiplications, so I can factor out this x1 plus y1. So I do that in one step here. With a type of parentheses that we will try to fix. But generally, you'll use a couple vector space axioms to get to this point. One for rearranging the order of addition, and then one for factoring things out. So just keep that in mind. Right? Hence, sketch of proof. I'm not doing the 2 axiomatic steps here. Okay, and now this, I know these coefficients, x1 plus y1, these are going to be elements of the field F, because in the real numbers and the complex numbers, if I add 2 real numbers together, I stay in the real numbers. Same for complex. All right, so because of this, this is a legitimate linear combination of those vectors. Therefore, this is going to be in the span of S. We okay with this? So if you wanted a formal proof, this would take 2 lines. one for the axiom for associativity of addition, vector addition, and one for the axiom for this distributive rule, right? Sketch a proof, so I'm skipping over that. I believe the text does have a full formal proof for this. Okay. Now the next thing we need to do is show closure under scalar multiplication. So I need to start with a scalar, an f, and I need to start a vector in the span. So here, since x is in the span, I know there's these coefficients where I can write x in this way. Now we just play the same game. C times x. Well, x is this linear combination. And now I can use my distributive law to distribute the c across. Boop. And that would then be an element of the span because, again, the field f is closed under multiplication. Okay? Now, if you wanted to do the formal proof here, to go from here to here, you have to be a little bit careful with some of the axioms, and it actually basically requires doing an induction type proof that you can actually distribute the c across a finite sum. So keep that in mind. We're not going to force you to do any induction type proofs in this class, but that for completion of the idea. And then we end from the result follows from the subspace test. Here, you always need to include that. In a sketch of a proof, you technically don't need to include it, but because that tends to be something people forget, I will put that there so that you don't lose marks by not doing that. Okay, so now that we have this, it's a quite useful result, right? It means if I give you any collection of vectors that live inside some vector space, I can always build a new subspace by just taking the span of them. And this is actually a big part of the reason why we care about span for this part in the course, is it gives us a way to build new vector spaces in a meaningful way very quickly. The other reason is bases. That's coming soon. Okay. Linear independence. So, a collection of vectors, v1 through vn, in a vector space V is said to be linearly independent if the only solution to this is the solution where all the coefficients are 0. Okay? So effectively, what linear independence is really telling us is, in a hand-wavy sense, that none of the vectors kind of point in the direction of any of the other vectors. Now that statement's not strictly true, because you need the linear combination to make that exact. And yeah, so two vectors, like you might have a vector space where all the vectors individually point in different directions, but it still isn't linearly independent. But that's kind of the idea. Like none of the, like I need all the vectors individually. If I throw away one, I'm actually losing information. That's kind of the key idea there. If a set's not linearly independent, we say it's linearly dependent. Now again, so that we can have nice things and we don't have to sound like lawyers when talking about theorems, by convention, the empty set is linearly independent. Why? Because we said so. In particular, if the empty set was not linearly independent, then that leads to issues with some of the theorems involving bases. So, for instance, the vector space that only consists of the zero vector wouldn't have a basis if we threw away this convention. Okay, so a proposition. A subset S, collect a finite subset of these vectors v1 through vk of a vector space V, different V there, is linearly independent if and only if at least one vector in S is a linear combination of the other vectors in S. Okay, so the proof of this is assigned reading. I do actually suggest you try proving this proposition on your own. It's a very good spot to spend some time to try to learn these ideas, is to just do the problem, right? And the idea here, for the forward direction, if it's linearly dependent, that means there's a non-trivial solution. Figure out how to use that non-trivial solution to write one of the vectors as a linear combination of the other ones. Right? Conversely, if at least one vector in S is a linear combination of the other vectors, well, suppose that that vector is v1. Without loss of generality, you can do that. That means I can write v1 as a weighted sum of v2 all the way through vn. Plug that into this expression here, and then try to build a non-trivial solution to this linear combination is the zero vector. Right? That's what you need to do. think about how to actually implement that on your own and make it formal, and then go do the assigned reading. That's my very strong suggestion here. The way to learn this material is to get your hands dirty. This is a very good example of a question that's theoretical in nature. That could be like a quiz type question. Well, probably want to do the if and only if, because it's a fair bit of work there. But it's the type of thing that you're expected to be able to do. So practice now, and then it's kind of like a safe learning ground for that material. Okay, is this set linearly independent? I don't know. Let's go find out. So if I want to determine if something is linearly independent, I have to appeal to that definition. So explicitly what I need to do is I need to examine the equation 1, 0, 0 with some scale factor plus the second vector with some scale factor plus the third vector with a scale factor is equal to the 0 vector. Now here, these vectors are elements of Rn. If I'm not telling you what vector space to give you, and they're kind of standard vectors with respect to a commonly used vector space, you're just going to use the normal vector operations there. So here, what we're really asking is this linearly independent in R3? So that's our 0 vector, right? Okay. So now we just need to solve this. You have options. You could write it as a matrix, right? You could do your 1, 1, 1, 0, 0, 1, 0, 1, 1. Augment it with zeros. Row reduce, see if this part becomes the identity matrix. That's perfectly valid, but again, that's too much work. Here, if I just eyeball it, I can try to pick apart the question. If I look at the second component of the vector, that equation reads c is equal to 0. Okay, now we're cooking on gas. If c is equal to 0, this term doesn't matter, it goes away. Okay. Now, if I look at the third equation, the third equation tells me b is equal to 0. Hey, this term goes away, right? So this causes that to go away, and so color coding, that causes that. Now the last one, the top equation, reads a is 0. Done. Linear independence. No row reducing. In general, you should actively avoid trying to do the row reducing algorithm, because it's the algorithm we teach you is O of n cubed. If you're not familiar with big O notation, for a 3x3 matrix, you're basically doing 3 to the third operations kind of thing. So it's not very efficient. So if you can avoid using it, try it. So yep, so that's how to solve this one. Same thing, but now we're using matrices as our vectors. So again here, since the question doesn't say what vector space we need to work in, we need to infer what it means. So here, since these are 2x2 matrices, this means M2, 2 of R. Okay, so we do the same game. We set up an arbitrary linear combination of these vectors, and we set it equal to the 0 vector. Oops. Freudian slip of saying equals and writing equals and doing it again at the same time is equal to the 0 matrix. Okay. Now this one, it might not be immediately obvious how I can rewrite this as a matrix equation if I chose to take that path. But what you can really the way you can really think about this is two matrices are equal if and only if the individual components are equal. And setting the individual components equals gives me a system of equations. So here we get a times 1 if I look at the first component, plus b times 1, which I'll just write as b, plus c times 1 is equal to 0. If I look at this component, the a term goes away, I get b, the c term goes away, is 0. Hey, that's nice. If I look at this term, a term goes away, b term goes away, but the c term remains. And if I look at the third component, I get a plus b is equal to 0. Okay. So later we'll have isomorphisms and some embedding maps and that kind of, no, not embedding maps here, but that will have different tools where you can turn these into vectors by like using coordinate vectors, that kind of thing. But for now, this is the natural way to read this off. Now these two lines tell me B and C are both 0, right? And if B and C are both 0, if I plug these into the first and the last equation, the conclusion we get from both cases is that A is equal to 0. All right? This means that the set will be linearly independent. Okay. So, now a couple more examples. Determine if this set is linearly independent or linearly dependent. If it is linearly dependent, find a subset that's linearly independent and has the same span. Yeah, so the idea here is if I give you way too many vectors so that you break linear independence, you can throw away things, maintain linear, or to become linearly independent, but maintain the same span. Okay, so if I look at this, the first two vectors, well, we'll do this one slightly differently. If I look at this, this vector is the only one that does anything for the second component. And these two vectors only do something for the first component, right? So clearly, one of these two vectors we don't need, right? So to give the formal determine if it's linearly independent, we'll say no, it's not linearly independent. Actually, not no. We'll just say linearly. Damn it, bad word. We'll say linearly dependent, right? Because I can just say 1, 0 plus minus 1, 0 is equal to 0. Now, I can't throw away the second one, or sorry, the third vector, because if I do, I'm losing information about the second coordinate. But I can throw away either this one or this one. And if I do that, I'm going to maintain linear independence because the second component would require its coefficient to be 0. And since these only have one term, it requires the first, its coefficient to be 0. So the answer is there are two correct answers. 1, 0, 2, 2. Or minus 1, 0, 2, 2. Okay. Now, in general, the way that you would solve this, if you had no idea how to approach it, and the way that I do in the slide solution, is you take an arbitrary linear combination of these coefficients, of these vectors, C2, 0, or 2, 2, set this equal to 0, 0. Solve for A, B, and C in terms of each other, right? So find an expression here. And then the terms within here that have arbitrary parameters in them are going to correspond to the vectors we can throw away. So I'll show how to do that in slide form. And this is how to approach these types of problems if it's not immediately obvious. So looking beyond this simple example, this is the methodology that you would use to solve hard problems. So, solution. We need to look for non-trivial solutions to this. We turn this into a system of equations, right? We want to solve this for A, B, and C. So if you look at it, I know C is 0 immediately, and then if C is 0, I know A is B. So here's this in overly large numbers of words. If I put it together, I know C is 0 and A is B, and in order to have non-trivial solutions, as long as A and B are both non-trivial numbers and the same number, then I get a non-trivial solution to the system of equations. So what I did is I introduced this non-zero constant t that is equal to both A and B that chases this out here. So since there's a non-trivial solution, we can say it is very clearly linearly dependent, formal proof. And now if I want to extract a linearly independent subset, we have to be careful which vectors we can throw away, right? I cannot throw away the vector associated with C, but I can throw away all vectors other than one of them that are associated with the parameter t. So namely, I can throw away this one or that one. Okay. And I'll just throw this up. You can pause the slide and look through it here, but this is what we just talked about kind of in words just previously. And leave that up for a little bit longer. Okay, last slide. Now that we have linear independence and we have spanning sets, we can talk about what a basis is. So a basis for a vector space V is just a linearly independent subset of V that also spans V. Okay? So spanning means that everything in V can be expressed as a linear combination of my bases. And linear independence means that there's a unique way of doing that effectively in this context. So we will talk more in detail about the statement I just made regarding linear independence, telling me something about uniqueness, but that's really why we want a basis, right? So to put it kind of in very practical terms, a basis allows you to get a handle on a abstract vector space. I might not know what the vector space does. It could be complex. It could do some really weird things. But if I have a basis, then in some sense, all vector spaces of the same dimension kind of act the same. And we'll quantify that once we get to the isomorphism theorems. But yeah, bases, honestly, if it wasn't for bases, we probably wouldn't be able to teach linear algebra at the undergrad level. Okay, so very key concept. You probably already know it, but make sure you know what a basis is. Make sure you know how to test linear independence and spanning. All right? Okay. So theorem, every vector space, whether finite or infinite. So finite should probably not be super surprising, but infinite vector spaces, these have a basis. Right? So every vector space has a basis. We're not going to prove this, but the idea, so not going to prove this, So this idea comment, this is the thing I said in words up here, right? So without bases, we basically don't really have the ability to do much with the vector space. Okay, so assigned reading, read those parts of the course notes, go back and actually try the questions that I recommended solving in the lecture itself. Practicing proving those types of theorems is extremely important for this class. And if you're just reading the theorem and nodding and going, yep, I know how to do that, that's not setting yourself up for success. So do actually try proving some of those theorems. Struggle with it a bit, work your way through it, make mistakes. That's how to get good at math. Nevertheless, we have a meme. Fellas, if your basis isn't linear independent and it doesn't span your vector space, it's not a basis. It's a random collection of vectors. Okay, so that is it for today's lecture. I managed to get it 7 minutes shorter than normal. So, yep, I will talk to some of you later. The other section, I don't know if I'll see you guys again in person. Well, the exams, but best of luck. Have a good weekend, all that good stuff.